In today's lecture at Medical Sciences, we're going to discuss with you the resting membrane potential and action potentials across the neurons, whereby we are going to look at neuron as part of excitable tissues. For example, we're going to see that excitable tissues, these are tissues which can respond to stimulus by causing electrical signal. And these excitable tissues, we're going to see that they include neurons, then they include muscles, whereby muscles are categorized into skeletal muscles. Then we have smooth muscles and cardiac muscles. So these are the excitable tissues which respond to stimuli by sending electrical signals. But in our session, we are going to zero on the neurons, whereby we are going to look at the resting membrane potential of the neurons, how it is maintained. Then we shall look at how action potentials develop by looking at the resting membrane. Then how do signals or impulses sum up to reach the threshold value. Then the threshold value shall be the firing level. Then we shall also see the peak, what we call the overshoot of the neurons, whereby under action potentials we shall see the resting membrane potential, depolarization, and repolarization. So this is polarization, which we shall look at. We're going to talk about depolarization, how cells become depolarized to fire an action potential, and then we shall see how they get repolarized. That is, we are going to discuss it. Then from there we shall see how the impulses are transmitted across the synapse so that neurons communicate with neurons for signals to be transducted. And as we begin, we always remind you to subscribe if you haven't. If it is your first time or you haven't subscribed, to support this good work, please go to the subscription button and subscribe. Like the video, and then share your comments and to others so that they can continue learning. So we're going to look at the membrane potential. And the membrane potential of neurons, we are going to tell you that its membrane potential is negative 70 millivolts. For skeletal muscles is negative 90 millivolts, because membrane potentials are measured in millivolts, whereas smooth muscles, it is negative 60 millivolts. Then cardiac is also negative 90. This is negative 90, negative 60, and negative. So cardiac and skeletal muscles have the same membrane potential, whereas smooth muscles have the least membrane potential, which is negative 60. Then neurons is negative 70. So it is very important to know the resting membrane potentials of different excitable tissues. And this resting membrane potential, the word comes from resting. The cells are not transmitting any impulse. They are at rest. And why do we call it, what is it? The resting membrane potential is whereby the electrical charges, here we see when it is at rest when the electrical charges outside they are positively charged and inside negatively charged. That is a resting membrane potential, which is whereby the electrical signals or ions outside the cell is positively charged due to accumulation of sodium ions. This positive charge outside is due to high concentration of sodium ions, and the inside negative is created by the potassium and the negatively charged substances like proteins and phosphates. That is what we call the resting membrane potential. And at this point, there is no impulse transmission. there is no impulse transmission. So after knowing this resting membrane potential, that it is the potential or the electrical signal of the cell whereby outside of the cell is positively charged and inside the cell is negatively charged. This is the cell membrane, then this is the phospholipid bilayer, and when the outside is positively charged and inside is negatively charged is what we are calling resting membrane potential. This is resting membrane potential. And this is due to high accumulation of sodium ions outside the cell, then with potassium ions inside the cell. Even outside, we also find there chloride ions, and inside here we find there like calcium ions, the proteins, and the phosphates. And these ones, for them, they are negatively charged. So these are the ones we find inside the cell, then these ones we find them outside the cell. And even the bicarbonates can be found inside the cell. So we are seeing this issue on how can we maintain, how is this resting membrane potential of the cells or the neurons maintained? Because today we are talking about neurons. So we are going to say that one of the key factors which maintains the resting membrane potential is the sodium stroke potassium ATPase pump. That this sodium stroke potassium ATPase, which is an example of a primary active transport, it has two receptors outside, and these receptors bind to potassium, whereas the three receptors inside bind to sodium ions. It has three receptors, so it carries three sodium ions. It has receptors, three of them inside, then outside it has two receptors for potassium ions. So in the presence of energy, in form of ATP, when there is energy, when during hydrolysis of ATP, whereby ATP is hydrolyzed to ADP plus phosphate in organic, the energy created is going to spin the three sodium ions which are inside on the receptors, and they pump them out. So we are taking outside the three sodium ions, and these two sodium ions which are on the receptors inside, they are brought inside. So we are pumping out three sodium ions, and we are bringing inside two potassium ions. And this creates a negative charge inside. Because you're inside of the cell, we are losing three. And imagine you're losing three, then you're bringing in, so it is a negative 3 plus 2. Negative 3 sodium ions plus 2 potassium ions. The end result, you shall have a negative 1. So here inside we are demanding a negative 1, and this negative 1 causes outside the cell to become positively charged and inside the cell to become negatively charged. So the first mechanism of maintaining resting membrane potential of cells is by sodium stroke potassium ATPase, which pumps three sodiums from inside to outside against the concentration gradient, because we see the sodiums are in outside there are many and inside there are few. So the little which are inside are also being pumped out. That's why we need energy to pump against the concentration gradient, and we bring the two potassium ions. So we remain with a deficit of negative 1, which causes inside the cell to become negatively charged and outside positively charged. So that is mechanism number 1. Mechanism number 2 is by these leakage channels. These ones we call them leakage ion channels, whereby among the leakage ion channels we have leakage channels, whereby one of it is the sodium leakage channel. So this is sodium leakage channel, and this sodium leakage channel, it allows also the sodium ions to leak inside the cells by passive transport. But this is not so much important like the potassium leakage channels. These ones, we are calling them potassium leakage channels, whereby after having much concentration of potassium inside, if we have much potassium inside accumulating, there is high concentration, these potassiums tend to leak out of the cell passively. This is passive transport. Because they are open or they are negated, so after the resting membrane potential, still some of the potassium ions leak out of the cell. And when they leak out of the cell, these ones can lower the membrane potential even to negative 90 millivolts. And this one can result into what we call hyperpolarization. Because the polarized state is at negative 70, so when you go to negative 90, that is what we call hyperpolarization. So due to continuous leakage of potassium ions, yet the sodium don't leak so much, there is little leakage. So it also creates a difference or charge difference, which maintains the resting membrane potential. So this hyperpolarization is corrected by the small leakage of the sodium ions, which restores the membrane at negative 70 millivolts. So this is what we can discuss about maintenance of resting membrane potential by three mechanisms, that is sodium/potassium ATPase pump. Then we have seen leaky sodium channels and leaky potassium channels. But remember, inside the cell, apart from having potassium, we told you we have negatively charged proteins and negatively charged phosphates. So these negatively charged ions, for them, because they are big in size, they cannot leak out of the cell. So we lose the potassium, whereby maintaining negatively charged substances like proteins and phosphates. And this one further creates a negative charge, which brings about hyperpolarization. So hyperpolarization, well, as we are moving on, we are going to see, can be due to leakage of potassium ions passively via leakage channels, together with failure of the negatively charged substances like proteins and phosphates to leak out of the cell because they are large in size. So that is how we can talk about it. So after seeing the maintenance of resting membrane potential, outside the positively charged, inside the negatively charged. So now we are going to look at how do action potentials develop so that they can be fired. And an action potential occurs in phases whereby we shall have the first, when an impulse is arriving, when an impulse comes in the cell, we have the impulse arriving, that is a change in stimulus. It finds when the cell is in the resting membrane potential, whereby outside of the cell is positively charged and inside is negatively charged. And this is what we call that the cell is in a polarized state. Is polarized, and this one we said the polarized state of neurons is at negative 70 millivolts. That is where it is maintained by these three mechanisms: sodium/potassium ATPase, leaky sodium channels, and potassium channels, plus the negatively charged proteins and phosphates failing to leak out of the cell. So this is what we call resting membrane potential. So when an impulse arrives at the cell, it must cause the change in the electrical signal, whereby it can excite this resting neuron, and after becoming excited, it brings about what we call at the neurons. There are those neurons which produce what we call, if I have a neuron here, there are those which are excitatory. They act by producing EPSPs, excitatory postsynaptic potential, where others, we have other type of neurons. For them, they produce what we call inhibitory postsynaptic potential, like the GABA. Those which have the GABA receptors, they produce IPSPs. Whereas those which are excitatory, like the glutamate, they have excitatory postsynaptic potential, that when the neurotransmitters are released, they come and excite the postsynaptic, leading to propagation of an action potential, whereby these ones inhibit by causing inside to become negatively charged. So when during impulse transmission, when a neuron is excitatory, they must sum up. They have to sum up to reach what we call threshold value. And it is at threshold value where there is a firing level, where an action potential can be fired, or where the cell, so when the cells become depolarized, arrival of the impulse cause the outside of the cell to become positive, to become negatively charged, whereby inside the cells become positively charged. How? Because when an impulse arrives, it causes the gated, we have what we call gated sodium channels. These are sodium channels, whereby these sodium channels, they have what we call the inactivation gate, and the inactivation gate is always open at the membrane state, then closed outside. So when an impulse arrives, it causes the opening of the activation gate. So the activation gate of the gated, high voltage gated sodium channels open, and when it opens, it allows influx of sodium ions. Remember, this inactivation gate is also partially open, so it will allow the entry of sodium ions inside the cell. So depolarization of the cell is brought about by opening of sodium gated channel. So this one is due to opening of sodium gated channels. So when the sodium gated channels, if I have another sodium gated channel here, it opens, allowing more entry of sodium ions. So we are seeing sodium ions are entering inside the cell from outside to inside. So we are losing outside sodium ions to inside, hence making the outside to become negatively charged and inside of the cell to become positively charged. And this is what we call depolarization, whereby the cell becomes depolarized due to the opening of sodium gated channels, leading to influx of sodium ions inside the cell, hence outside becoming negatively charged. So the negative charge is brought about by the loss. We are losing the sodium ions without adding. That is why we call it negatively charged. Then inside becomes positively charged because they are gaining the sodium ions, but they are not losing anything from the to outside, hence becoming positively charged. And this is what we call depolarization of the cell. And if this depolarization occurs, whereby there is more, the postsynaptic neuron is being excited, and inside of the cell become positively charged and outside negatively charged. This one is going to, when they sum up to reach the threshold value, they fire an action potential. And types of summation are, we have under summation, we shall tell you that when this is the negative 70 millivolts, which is the resting potential, when an impulse arrives, it fires an action potential, but it might fail to reach the threshold level. This is the threshold. And there is what we call all or nothing. All or nothing law. That for an action potential to be fired, the stimulus should trigger the excitable tissue like the neuron to reach the threshold value, whereby the threshold value is always plus 10 or 15 millivolts. So if this is negative 70, we subtract like 15, so the firing potential is at 55. Negative 55 millivolts. That is the threshold value for neurons, because if I have 70, I subtract 15. That one becomes negative 55 millivolts. But an action potential to be fired after depolarization, it must sum up to reach the threshold value, which is negative 55. So if an impulse is weak and it does not cause the cell to be fired to reach the threshold value, an action potential cannot be fired. So if another one comes and fires and doesn't reach and comes back, still it haven't reached. So it must sum up, in summary, the action potential, the depolarization state of the cell must sum up to reach the threshold value. So if the first one fired and stopped here, it has to wait for another one until it sums up to reach the threshold value. So this is what we call all or nothing law. That an impulse or the excitability of the cell, the impulse should be able to excite the cell up to the threshold value so that an action potential can be fired. If not, then it is all or nothing. So all, it should sum up to reach the threshold value. Nothing, if it doesn't reach, if it stops at this level or at this level, an action potential cannot be fired. And the types of summation, we have what we call spatial summation and temporal summation, whereby under spatial, here you have one neuron. Here you have one presynaptic neuron and one presynaptic neuron simultaneously. It continues, it keeps bringing an action potential across the synapse until the threshold value reaches. That is what we call, that is temporal summation. So under temporal summation, temporal means you have one presynaptic neuron firing one postsynaptic neuron. So it keeps bringing an action potential, causing depolarization of the cell until threshold value is reached. That is what we call temporal summation. But spatial, here you have one postsynaptic neuron being fired by more than one presynaptic neuron. So this one fires here, this one fires here, another one can come and fire here. So when they sum up, they reach, and to reach the threshold value, an action potential is propagated. That is what we call summation. So summation is whereby the impulses, when the cells become excitable, they must add up to reach the threshold value, which is negative 55 millivolts. And the type of summation can either be temporal, whereby one presynaptic keeps firing the one postsynaptic to develop what we call EPSPs. And these EPSPs must sum up to reach the threshold value. Then under spatial, 1, 2, 3 presynaptic neurons simultaneously fires the production of excitatory postsynaptic neuron potential, which sums up to reach the threshold value. That is what we call summation of the cells. And when they have reached the threshold value, that is where here an action potential can be fired to reach a peak. This one is a peak. And for the nerves, it goes up to plus, maximum is 35 millivolts. 30 to 35 is the peak of the action potential for neurons. So it reaches the peak. So we shall see how it will cause repolarization. So this, from this point to this peak, is what we are calling action potential being firing. So the firing point is at the threshold value, which is always 10 to 15 plus 10 to 15 millivolts. So after the cell becoming depolarized, we have seen they must sum up the EPSPs, and these EPSPs, which we are calling excitatory postsynaptic potential, should be greater than inhibitory postsynaptic potential for the cell to fire an action potential so that it can propagate. So after firing of an action potential, due to the opening of sodium gated channels, because one thing I want you to capture is that the sodium gated channels, they are fast acting, they quickly open and quickly close. That is the property of sodium gated channels. So for when an impulse arrives, they quickly open and quickly closes, which is different from potassium. For the potassium, they take long to open and even take longer to close. So that's why we are seeing the depolarization of the cell is brought about by the sodium, which quickly opens in the presence of an impulse and quickly closes. So after firing an action potential, they quickly close. At this point at the peak, they are fully open, then they start to close. And this one will lead to what we call depolarization. This one will be depolarization. And this one, depolarization, is brought about by closure. So depolarization is due to closure of sodium ions. The sodium ion is closed, then this is sodium ions, then the potassium ions open. The potassium gated channels open. So we are seeing after depolarization and an action potential is fired, the cell become repolarized, whereby again they restore the resting membrane potential, whereby outside the cell will become now positively charged and inside negatively charged. And we are saying this is due to the opening of, is due to potassium channel opening, which we said the potassium gated channels take long to open. So by the time the potassium channels are opening, sodium ion gated channels close. So closure of sodium ion channels and opening of slow acting potassium ion channel are the one that brings about depolarization, or restoring the membrane potential is due to the quick closure of sodium ions and slow opening of potassium gated channels, leading to the cell again to become positively charged outside and negatively charged, because here we are losing the potassium from inside to outside. Potassiums are moving from inside, but remember the sodium ions have closed, so there is no entry of sodium. So we are losing from inside, but nothing is going out. So the out becomes positively charged and inside negatively charged. And hence the peak goes back to the resting membrane potential, as we are going to explain it more there. Then after depolarization, there is what we call repolarization. It can cause repolarization. I can illustrate it here. Whereby after the cells have restored the membrane potential, there is what we call repolarization. The cell becoming, this one is hyperpolarization. It is what we call hyperpolarization. We can restore the membrane potential to the extent that it goes below the resting membrane potential, whereby under hyperpolarization is due to complete closure of sodium ions and full opening of the potassium ions. So when the potassium ions are fully open, we are going to see outside the cell becomes more negative. So outside the cell is more negatively charged, and inside of the cell is positively charged. This is what we call hyperpolarization due to complete closure. Here, the sodium ions were closing as potassium ions were opening. So there was no full closure. But here the sodium ions are fully closed. And because they are fully closed and the potassium ions are fully open. And this one leads to excessive loss of potassium ions outside the cell, and then it becomes more negative, leading to hyperpolarization. And the hyperpolarization state is at negative 90 millivolts. Negative 90. Then the repolarization is at negative 70 millivolts. That one is also important to note. Let me put them in different color for easy identification. That during resting membrane potential is negative 70. During depolarization, it is at negative 55 millivolts. That is the depolarization state. Then repolarization goes back to negative 90 millivolts. Then hyperpolarization, this one comes back to negative 70. Then hyper goes to negative 90 millivolts. So these are the values we can have for polarization, depolarization, repolarization, and hyperpolarization. So as we are nearly ending our discussion, we have seen many concepts under this. We are going to tell you, but we shall explain the other side, whereby we shall see how we restore the membrane potential. So as we are seeing how impulses are transmitted due to the formation of an action potential, we have been seeing that these neurons have what we call sodium ions. And when sodium ions open, sodium ion gated channels open, there is movement of sodium ions inside. Sodium moves inside, making inside to become positively charged and outside negatively charged. This is what we call depolarization. And when they become depolarized, when the neuron, this is the presynaptic neuron, then this is the postsynaptic neuron, this is the synaptic cleft. Then this is the vesicles in the impulse. So at the arrival of an impulse, when an impulse arrives in the neuron, it causes the depolarization, whereby there is influx of sodium ions. And when sodium ions enter inside of the cell, become positively charged and outside negatively charged. And this depolarization must sum up to reach negative, that when it sums up and reaches the peak, which is at 30 plus 30 millivolts, which is the peak, it causes opening. It is going to cause opening of this calcium, because at this level we have the high voltage gated calcium. These are high voltage gated calcium channels, and in the cleft we always have the calcium channels. So when the neuron becomes depolarized, and after becoming positively charged, to reach at positive 30 millivolts, it will activate the opening of the high voltage gated calcium channels, and this one will lead to influx of calcium ions inside the neuron. And when calcium ions enter inside the neuron, due to the high voltage created by the entry of sodium ions, it is going to cause this increase in the concentration of calcium ions inside the cell, causes the movement or brings about contractions, leading to the vesicle containing neurotransmitter fusing with the membrane, leading to release of neurotransmitter by exocytosis. This one is exocytosis. They are released by exocytosis into the cleft, whereby they come and attach on the receptors on the postsynaptic neuron, and when they attach, they lead to the influx. Here in the cleft you have sodium. The sodium ions will enter, causing inside to become positively charged and outside negatively charged, hence leading, when they sum up, they come up with excitatory postsynaptic potential, and these ones, when they reach the threshold value, they fire an action potential. That is how nerve impulses are transmitted across the synapse. One is that upon impulse arrival, it causes the influx of sodium ions inside the neuron, hence becoming depolarized, whereby inside is positively charged, outside negatively charged. And when it reaches this point, it's going to trigger the opening of high voltage calcium channels, leading to influx of calcium in the presynaptic neuron. And this calcium brings about contractions or movement of the vesicles towards the presynaptic membrane, and diffuses to release neurotransmitter by exocytosis. Neurotransmitters can be acetylcholine, norepinephrine, depending on the type of the neuron. And when these are released, they come and attach on the receptors on the postsynaptic. And when they attaches, either they can cause excitatory or they can cause inhibitory. How can they cause, if it is an inhibitory like GABA, instead of causing depolarization, it causes hyperpolarization. That is for IPSPs. That is inhibitory. So this is how action potentials propagate, that when they are excitatory neurons bind, cause influx of sodium ions, and when they sum, or they have to form EPSP, what we are calling excitatory synaptic potential, when it sums up to reach a threshold value, action potential is propagated, hence an impulse is transmitted. So I can end this session by drawing the illustration of the graph, whereby I want to show you how the different peaks and stages on the action potential. If I have a graph like this, this is the graph I'm going to have in this session as I'm summing up our discussion, whereby this one is going to be the membrane potential in millivolts. This one is going to be time in milliseconds. Time is measured in milliseconds. We are going to have what we call the resting membrane. Then we are going to have another which we call threshold value. This is going to be threshold level. Then this one is going to be peak. And this one is at negative 70 millivolts. This one is at negative 55. This one is at positive 30 or 35 millivolts. So what we are going to see is that arrival of an impulse, if there is an impulse which is exciting our neuron, it is going to cause the membrane potential, it is going to cause depolarization. And when depolarization happens, it has to sum up to reach the threshold value. This is summing up, whereby the depolarization sums up to reach the threshold value, and at this point, this is what we are calling the cell becoming depolarized, and it reaches the threshold value, it is going to fire an action potential. And this is what we discussed about the all or nothing, that an impulse should be able to sum up to reach the threshold, either by temporal summation or by spatial summation. When they reach the threshold value, they fire an action potential. And this is what we are calling the peak of the action potential. So this is action potential, and this action potential is brought about by sodium gated channels opening, allowing influx, which is bring about that. So the peak is at plus 30 millivolts. And after opening, we say the sodium channels they quickly open and quickly close. So at the peak, after they reach at the peak, they start closing. As they start closing, remember potassium are slow to open. So as the sodium ions are starting to close, the potassium are starting to open, which will bring about repolarization. So this region is what we are calling repolarization. And this repolarization is due to it is contributed by the closure, starting to close of the sodium ions and the opening of potassium ions. So here it is repolarization is due to the potassium gated channels, they are open. They have started to open as we have started closing the sodium, leading about repolarization. And during this repolarization, here, even though you bring an impulse which is of higher threshold than even the former, we cannot fire an action potential. So during this period, from here up to here of repolarization is what we call absolute refractory period. Absolute refractory period is the period where a nerve cannot fire an action potential, when even other impulses of stronger intensity come. Why? Because the cell is restoring the membrane potential. So it is during repolarization whereby the cell is restoring the resting membrane potential. And during that time, the sodium ion channels are fully closed. They cannot open, so an action potential cannot be fired. That is during absolute refractory period. Then, after restoring the resting membrane potential, we had what we call hyperpolarization, whereby the complete opening of the potassium channels and the complete closure of sodium ion channels can bring about hyperpolarization of the cell, whereby the neuron becomes hyperpolarized. This is what we are calling hyperpolarization, and hyperpolarization occurs at negative 90 millivolts for neurons, whereby the cell is hyperpolarized due to complete potassium ions gated channels opening. After becoming hyperpolarized, during this period, we can see what we call relative refractory period. And the relative refractory period is the period whereby if an impulse which is coming is greater than the one which has passed, an impulse can be, or an action potential can be fired before even restoring the membrane potential. That is what we call relative refractory. So you should be knowing the difference between absolute refractory period and relative refractory period. Absolute means even when you bring an impulse of stronger stimulus, it cannot fire an action potential. Then relative, if an impulse, if she has higher intensity than the one which has been being transmitted, an action potential can be fired, and that is during hyperpolarization state, whereby we said under hyperpolarization state, the inside of the cell become more negatively charged. So we have seen here we are summing up to reach the threshold whereby this one is going to be the firing level. Then an action potential is fired to reach the overshoot, or what we call the peak. You can call it the peak or overshoot. And then the sodium channels close, leading to repolarization, restoring the resting membrane potential due to the closure of sodium ions and potassium ions opening. Because we said potassium slow to open and even take longer to close. And because they take longer to close, they are the one that contributes to hyperpolarization, whereby you see sodium ions have completely closed, but potassium ions are continuing to fully open, leading to increased loss of the potassium ions, leading to hyperpolarization, which is at negative 90 millivolts. Then it is again restored. And we have seen refractory periods. So this is what we can discuss in this session, whereby we have looked at the excitable tissues and their resting membrane potentials. We have seen mechanisms how they are maintained, whereby it is sodium it pays stroke potassium it pays pump, then the leaky sodium and the leaky potassium channels together with negatively charged proteins and phosphate which cannot leave, hence maintaining the resting membrane potential. We have seen the action potentials, whereby when an impulse arrives, we see the resting membrane potential turning to depolarization state due to opening of sodium ions, which quickly opens and quickly closes. Whereas repolarization is brought about by the slow-acting potassium-gated channels, which slowly opens and slowly closes. So as the sodium ions have completely opened and quickly closes, the potassium ions start to open, leading to restoration of the resting membrane potential. Then hyperpolarization we have seen is due to the potassium ions taking longer to cross. Here sodium ions are fully closed, but potassium ions are still open. So here it brings about the inside of the cell to become more negative at negative millivolts, 90 millivolts, which is hyperpolarization of the neurons. And I have seen how an impulse is transmitted across the synapse. Then we have ended up with the graph summarizing what we have explained here, showing you the threshold value, the peak, and the repolarization state together with hyperpolarization. Thank you so much for learning with us at Medical Sciences. May good Lord bless you.